I now call to order the Society's 2,423rd meeting in the 149th year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., dedicated to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests to tonight's lecture by Henrik Christensen, communicated by Zoom and YouTube. We will begin with a few announcements, followed by a reading of the minutes of the 2,422nd meeting and a lecture by Rajesh Rao on when AI joins the human brain. We'll then turn to this evening lecture, followed by a question and answer period. When the Q&A session is done, I will thank our speaker. I will make a few closing announcements. I will bring you up to date on the fall schedule. I will thank those who make PSW possible, and then adjourn the meeting. Before we begin, let's please thank the sponsors of the 2019-2020 lecture series, the Policy Studies Organization in cooperation with the American Public University, and a generous donor who has asked not to be named. Please give them all a round of applause and thanks. And tonight, let's also thank the sponsor of this evening's lecture, PSW Erica Kane, a physicist, software engineer, and CEO of CenturyLink. We all thank you very much, Erica, for your support of PSW. And we look forward to when we can resume in-person meetings and join you again at the reception and dinner and the social hour. I am pleased to announce that the following new member has been elected to membership in the Society. Tonight's speaker, Henrik Christensen, whose background and interests will be clear in small part to all of us from tonight's proceedings. Please join me in welcoming Henrik to membership. Henrik, welcome.
Thank you, Larry.
Okay. Recording Secretary James Heelan will now read the minutes of the 2,422nd meeting and Rajesh Rao's lecture on when AI joins the human brain, delivered to the Society by Zoom and streamed to the PSW Science YouTube channel on Friday, June 5th, 2020. James.
Hi, good evening. On June 5th, 2020, by Zoom video conference broadcast on the PSW Science YouTube channel, President Larry Milstein called the 2,422nd meeting of the Society to order at 8:00 p.m. Eastern Daylight Time. He announced the order of business, that the evening's lecture will be live streamed on the internet, and welcomed new members to the Society. The recording secretary then read the minutes of the previous meeting. President Milstein introduced the speaker for the evening, Rajesh P.N. Rao, Professor of Computer Science and Engineering and co-director of the NSF Center for Neurotechnology at the University of Washington. His lecture was titled, When AI Joins the Human Brain, Brain Coprocessors for Restoring and Augmenting Human Function. Rao asked, what would be possible if a computer were connected directly to the human brain? He posited such a connection could enhance our human abilities with robotics, facilitate learning skills by downloading information directly to the brain, and convey thoughts telepathically. The Center for Neurotechnology is currently exploring these questions with brain coprocessors, which use artificial intelligence to interact directly with the brain. A brain coprocessor reads from and writes information to the brain, and in some cases, to and from an external information source or actuator. Rao's lab is exploring electroencephalography, or EEG, electrocochleography, ECOG, and microelectrodes as a coprocessor technology. EEG uses electrodes attached to the scalp to record small electrical fluctuations, which are then decoded to record brain activity. ECOG receives and transmits information directly on the surface of the brain. Microelectrodes are implanted inside the brain and allow scientists to attempt to receive and write information directly to and from targeted neurons. In 1988, scientists successfully decoded intended activity from neural activity. In 2012, University of Pittsburgh researchers successfully enabled a woman with tetraplegia after 13 weeks of practice to control a prosthetic arm with 7 degrees of freedom. Coprocessors may also be used to bridge disconnected areas of the brain, such as after a stroke. One of Rao's collaborators successfully completed such a bridge by reading from one area of an animal's brain and writing it into another. After 2 days of connection, the researchers observed EBM plasticity strengthening the connection. Rao said, eventually, an artificial bridge may sufficiently strengthen brain connections such that they function without a coprocessor's assistance. ECOG can facilitate the brain's direct control of software functions. As proof of concept, Rao and his colleague were able to use ECOG to read activity in the Broca area of the brain generated by a subject's repetition of the word move to move a cursor on a screen, with only 30 to 60 minutes of the subject's practice. As subjects practiced, they became able to move the cursor using only imagined speech. Rao was optimistic this technology could eventually be used to assist people who have lost motor functions to communicate. EEG has also shown sufficient to extract information about imagined movements. In 2008, researchers were able to train subjects for several days and to read the subject's imagined feet movements with EEG to navigate virtual mazes. That same year, researchers were first able to use EEG to control a robotic avatar to pick up and move objects. Rao called the feat Iron Man 1.0. In 2010, Rao asked whether coprocessors could enable brain-to-brain communications. Transcranial magnetic stimulation, or TMS, uses an induced magnetic field to penetrate the skull and induce electrical current in the brain. Researchers have been able to use TMS to control certain motor functions and the visual cortex. Rao said TMS is limited by the precise brain mapping and instrument placement required for it to perform the intended function. Nevertheless, in 2013, Rao's team demonstrated proof of concept by using EEG to read Rao's brain, to write with TMS onto his collaborator's brain, and control the collaborator's hands to play a simple video game. The team used the same concept to stimulate the subject's visual cortex to communicate answers to a series of yes-no questions. In 2019, Rao co-authored a Scientific American paper on their success in creating a multi-person brain net used to collaboratively play a Tetris-like game. That work explored the subject's ability to discern the relative value of information received from multiple brain sources. Rao concluded by looking into the future. He is currently researching use of coprocessors to train artificial neural networks. This work could potentially lead to neurological therapies for people who have experienced stroke and spinal cord injuries. The speaker then took questions from the online audience. One member asked how optogenetics fit into the taxonomy of technologies to rewrite the brain. Rao said optogenetics is used to change genes that allow imaging of individual cells and neurons. It is currently very invasive and only used in animals. Human use will depend on the ability to do so safely and less invasively. Another member asked why there seems to be a significant delay between coprocessing advancements and commercial availability. Rao answered he believes hurdles include legal liabilities and the need to improve the robustness of these technologies outside of laboratory settings. After the almost hour-long question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 10:23 p.m., President Milstein adjourned the meeting. The temperature in Washington, D.C., 29.5 degrees Celsius. Weather clear. and viewing through the live stream on Zoom, 38. Viewing on the PSW Science YouTube channel, 55. Respectfully submitted, James Elan, Recording Secretary.
Thank you, James. Sorry for the malfunction of our transporter, folks, but we're going to work on it in the next couple of weeks. It's basically a bad video channel, so and maybe a little lack of processing power, but I think the audio came through clear, so that's really the main part of the text. We'll keep it open for 48 hours for any comments or corrections that anybody has. Please send those to corresponding secretary at corresponding sec@pswscience.org. Again, send them to our corresponding secretary, Robin Taylor, at corresponding sec@pswscience.org. The email addresses that I mentioned tonight are all available readily on our PSW website at www.pswscience.org. We will consider the minutes accepted after 48 hours, and they will be posted to the website in due course. Now, just before I have the pleasure of introducing our speaker, let me mention that there are 3 ways that people will be able to ask questions. For those of you who are listening on Zoom, you have 2 options. And the one we prefer is that you raise your Zoom hand and let us call on you and unmute you, and you can ask a question using your own voice and your own microphone. Alternatively, if you're watching on Zoom, you can ask a question by text in the Zoom Q&A panel. Finally, for all of those watching on YouTube, you can ask a question in the YouTube chat channel, and that will be relayed to me, and I will sort through them and ask them. And with that, let me now turn to introducing tonight's speaker, Henrik Christensen, and his lecture on contextual robotics, making intelligent robots that serve society. Henrik is the Qualcomm Chair of Robotic Systems, Professor of Computer Sciences, and Director of the Institute for Contextual Robotics at the University of California, San Diego. He also is a member of the European Network for Excellence in Robotics, which he founded. And he is the main editor of the 2020 US Robotics Roadmap that will guide the National Robotics Initiative for the next 4 years. Previously, among other positions, Henrik was Distinguished Professor of Computer Science and Chair of Robotics at Georgia Tech. Henrik's research focuses on robotics and artificial intelligence, and among many interesting projects, he was principal investigator of Georgia Tech's team in DARPA's first self-driving vehicle urban grand challenge, where I believe they made a pretty good showing. He is an author of more than 350 scientific and engineering publications. He has co-founded several companies, including Robo Global and Robust AI. His work has been widely adopted by many companies and government agencies, and he's been featured frequently in major media reporting. Among many honors and awards, Henrik has been awarded the Joseph Engelberger Award and an honorary doctorate in engineering by Aalborg University. He is a fellow of the IEEE and the AAAS. He earned his MS and PhD in electrical engineering at Aalborg University in Denmark. Please hold questions for the question and answer period at the end of the lecture, and join me in welcoming Henrik to the Zoom. Henrik.
So first of all, thank you, Larry, for inviting me to give this presentation. I, of course, had hoped I could give it in person in DC. Very much look forward to coming, and unfortunately, that was not possible. And thank you for the opportunity for me to talk about sort of contextual robotics. And so the question I'm really interested in is, how can we use robots to empower people in their daily life? What will it take for us to be able to get to a place where we can, use this to compensate for various kinds of limitations that we have or that we grow over time, so that we are the best possible we can be. So let's see. So I want to start out by talking a little bit about some of the megatrends that I think are very much driving where robotics is going today. Then I want to talk about some of the technology that's also driving this, and then I want to dive in to show you some examples of how we are actually doing this for our daily lives. So if we look at sort of some of the megatrends that we're seeing, is very much that we all want to be able to buy products that are highly individualized. I don't want to have a card that's similar to everybody else, or a phone, or a product. Same time, we experience tremendous aging. Health is becoming more and more of an issue. Talk about that in a COVID period, where, of course, this is a huge challenge. Same time, urbanization. More and more of us want to live in urban environments. And then finally, the environmental impact. How do we actually make sure that we have a Earth 100 years from now that we can still occupy? I'm not going to talk very much about the sustainability in the environment in this lecture, but there's a lot of things that we could cover there. So if we start out by looking at manufacturing, so as I mentioned, there is a tremendous interest in being able to do individualization of products. So if I show you this BMW X Series car, which they're all built in Spartanburg, South Carolina, this particular car comes in 4 million different variants. So we all want different seats, different audio systems, different engines, all of this sort of adds up to 4 million different, which implies that they only make the same car every 2.5 weeks. So for that reason, we need to be able to orchestrate all of the manufacturing, all of the components in such a way that they arrive just in time, put into the factory, manufactured, and leaving. So they have an average storage time of 12 minutes. After, stuff arrives, 12 minutes later, it's mounted in a car and it's on its way out. To be able to do this, they need to have a very high degree of automation. And I'll come back and talk about how that is actually made possible. The other thing we're seeing is, of course, we're seeing significant aging of society. So the new prototypical audience are the baby boomers. They have significant resources. They want a high quality of life. As we sort of deteriorate over time, they want to know, how can we do compensation for this? And the entire industrialized world is seeing tremendous aging. So the world is aging 8 hours per day. So if you look at sort of the average age of the world population, it basically goes up with 8 hours every day. So for the foreseeable future, we will have more and more elderly people. And that would imply that as we grow old, we get various kinds of complications. We're not what we were when we were in our early 20s. How can we use robots to compensate for a number of this and assist people so that you can maintain a high quality of life? So I would love to be able to, when I retire, have a robot that would help me get out of bed, take a shower, get dressed, prepare a meal, and participate in social activities. That would help us being able to maintain sort of a high quality of life. So I'll talk a little bit more about that. We're seeing a tremendous amount of urbanization. 82% of the US population lives in an urban area, and it's even higher in Japan. And we are seeing a general trend that's going in that direction. It'll be interesting to see if that's still true in a post-COVID world, but certainly today we're seeing this. This has an impact on the environment. It has an impact on transportation. It has an impact on all sorts of aspects. And here it's interesting to see, how can we use robots to enable us to have the best possible quality of life, even when you live in very urbanized settings. Same time that we're seeing these societal drivers, we're also seeing some technology drivers. So if we go in and look at it, we started out having computers about 80 years ago. We got to cell phones, we got to significant data power. So, we have a tremendous amount of computing power in our cell phone. And now we're seeing this confluence of significant amount of computing power and mobility. And that opens up for a possibility of doing much better robotic or sort of cyber-physical systems that we've ever seen before. So the question we're interested in is here, how can we leverage this technology to enable people in their daily lives? Just to give you an example, if we look at here sort of a graph from CPAD that sort of shows evolution in camera technology. So the gray area that you're seeing down here is basically sort of traditional cameras that we had when I was young. Blue, we're getting to sort of compact digital cameras, and the orange is the smartphone. And just to give you a sense for how significant sort of cameras on smartphones are, here is an illustration of how significant this has been over the last 10, 15 years. So we've sold more cell phone cameras than we've sold any other camera technology today. For me as a technologist, the advantage is also they become incredibly cheap. So I can now go to Qualcomm and buy a 1 megapixel camera for $1, which implies that before I had to be very careful about how many cameras I use. Today, I don't have to worry about this. If you go and ask companies like Qualcomm or Intel or NVIDIA, they would say that you can get the processing power to process those images for about $9. So a camera with the associated computing substrate is about $10 in total, which opens up for very interesting opportunities. Same time, of course, we're getting new communications technology. Some of it we can do directly in these technologies, and some of it we might have to stream to the cloud. This is very much becoming possible by using interesting new technologies such as 5G and soon even 6G to think about this. But we can also do satellite communication and other modalities to build federations of systems that can collaborate on doing this. And I'll talk a little bit more about that later on. This also changes sort of how we think about systems. So in the 20th century, it was typically supply chain economics that drove how we've thought about things. So it was the steel mills, it was the big automotive companies that had the manufacturing capacity to go out and generate products at a very high volume. Like, Ford said, you can have any color of a car as long as it's black. And here we're basically getting to, they controlled very much the supply system. In the new economy, we've sort of changed it around. So instead, we're looking at a demand side economy. We are driving it as customers. It's driven by the individualization I talked about earlier and other things. So we're seeing this coming in with companies like Google, Uber, Amazon are all enabling this. So if we look at this a little bit sort of in comparison, it used to be that all the focus for a company was on resource control. Can I control my manufacturing? Can I control whoever is delivering to my company? Can I focus my internal optimization in such a way that I can optimize down to just-in-time manufacturing? I can optimize it using the standard Toyota model, and you could focus sort of on the product value. Now we're much more talking about resource orchestration. So if we look at Uber, most cases, they don't own the cars, but they can orchestrate it. That happens with a number of different companies where you're going in and looking at this. Same way you're looking at sort of the external interaction. How can I have this federation that collaborates and do really interesting things? And then the same, you're looking at the ecosystem value. So you don't have to own everything, but as long as you can optimize for that the entire ecosystem is doing the right thing, then you can still do these systems. So that's where we're getting to, where we're thinking about entirely new business models, entirely new ways of thinking about how do we build systems. So when I talk about a robotics ecosystem, we have to do all of this. We have to think about the automation. We have to think about the augmented reality. We have to think about the virtual reality. We have to think about how does this all come together to deliver a solution that is optimized for the customer in ways that we've never seen before. So that makes it very interesting. At the same time, we have to think about that we have very different customers. So this is a slightly dated graph, but it's only here sort of as a placeholder for me to tell you that the average 20-year-old American has spent 12,000 hours playing computer games. That's 2 years of their life with no sleep. So they're instant experts, they know exactly how to use their thumbs and all of this to be able to do this. But it also implies that when, for instance, we think about the future of user interfaces, the future of user interfaces should look like this. It should be iPad-like almost, very easy, flexible interface. It should not be tied to a particular product. It should be possible to use it for any product. So we're seeing a complete revolution because the gaming industry has sort of told us we should be able to use 3D, we should be able to use visualization, we should be able to do all of this and have plug and play. Not, when I grew up, it was plug and pray. Now everybody's used to that. It's very easy to actually integrate all of these technology into a unified framework that make it possible to build these systems. So let's start out by looking a little bit deeper into where robots actually used in sort of the manufacturing domain. So in manufacturing, we're used to seeing this where sort of the view is that we have all of these robots on the manufacturing line and there are no people around. That's a nice Hollywood dream that is not very much tied into reality. So still today, for the very highest degree of automation that we see, even in automotive factories, there's one robot for every 10 people. So we have fully automated the plate shop, fully automated the welding shop, we fully automated the paint shop. Once we get to where the products become individualized, there are very few robots. So that's still one of my big challenges. How can we actually do this? And the reason that the robots have been introduced in the plate shop and in the paint shop is mainly to improve the quality of the product. The cost is not that much different from using humans. It's mainly to drive up the quality. So when I was a kid, we had Monday cars and Friday cars and middle of the week cars. Now we have 7 days a week cars. And that makes sort of a tremendous difference for being able to use this technology. But one of the big evolutions we've seen are what we call collaborative robots. So robots that can work directly next to a person, they can basically share the same workspace and it's considered safe. So we saw this about 25 years ago. We started to see these robots. Puka Robotics in Germany was the first to build these. And the idea was that you can build a robot where you can collide with a human and it doesn't injure a human. So the question is, how do you figure out if it injures a human? What is the appropriate force to be able to do this? And basically people took the results from airbags. We have a number of airbags getting released every day. So we know how much can we actually use of force on a human body before you have to go to the ER. So that was being used to design these robots. Since then, this has grown to become the fastest growing industry where we have these robots, we deploy them next to people. They can basically be your buddy. And now it enables us to integrate robots into the workflow where we need very high quality. We use collaborative robots. Where we need sort of still more cognitive power, we would still have a person engaged. So here's an example, actually a BMW assembly line in Spartanburg, where you put on a water shield. So inside your door, there is this plastic shield, and you have to be able to go around and seal it, because if it's not properly sealed, the next time you go to the car wash, you will have water coming into the cabin. And if you just bought an expensive BMW, you're gonna be, really, people? So for that reason, it was very important to have a high quality here. These robots have better force control than a person has. And because of this, for that particular sort of sealing operation, you introduced a robot, whereas getting it in place and other things, you still use human. So this is an example in manufacturing where we go in and use collaborative robots to be able to do much better manipulation than we've been able to do before. The other thing where we've seen tremendous challenges is in being able to grasp objects. When you go to your regular grocery store, most of you probably don't think about it. You love the selection. That's because the average grocery store has 46,000 different items on the shelves. Being able to pick up all of these has for a very long time been very hard for people to actually have the dexterity, being able to recognize where are these objects, how would I pick them up? Through evolution in deep learning, so modern data-driven learning techniques, it's become possible for us to do much better grasping than we've done before. And that now enables us to do much better grasping. And that's why the big e-commerce companies can now do much better distribution than they could before, simply because we've gotten to a place where we can do much better grasping. Same time, we are able to build much better graspers and even much better robots by using 3D printing. We're now at a place where we can do multi-material 3D printing, and that enables us to build, for instance, more flexible end effectors. It enables us to build more flexible robots. It even allows us to sort of build robots with artificial skin so that we can sense the touch. So at the same time, we're getting to where we can do much better computer vision. We've gotten the cheap cameras. We're now at a point where we can do model-based tracking of objects like you're seeing here. So even though it's a transparent object, there's a very busy background, we can track these objects, and that enables us then to go in, grasp them, and handle them in a way that you've not been able to do before. So before we had very good robots that were sort of good mechanical systems, they were not very smart. Using this, we can go in, build in better perception, we can close the loop and make them collaborative so they can directly work with people. And we're even getting to a point where we can sort of do this on the fly. So here you're seeing detection of natural objects such as fruits. So here it's strawberries. 90% of all the strawberries consumed in the US are grown in St. Luis Obispo, north of LA. And being able to go in and pick these, especially in a COVID situation where we're in a crisis, we have a much smaller migrant workforce. So there it's of interest to be able to do this. So going in, seeing these objects, building a 3D models of these objects. And then once I have this, I can actually go in and I can 3D print. So here you're seeing an actuator that is basically an object that you go in, and as you sort of inflate it, it will grasp this particular object, and it will do it in such a way that it does damage the end product, like strawberries. So we can do fast, robust, and easy to clean end effectors using new materials technology that opens up for ways of doing this in a way that we've never imagined before. So that really drives a lot of the manufacturing, that we can close the control loop, we can do better perception, we can do much more flexible and safe end effectors, and enables us to do an entirely new industry. Of course, that then brings me to that we're seeing this also for distribution centers, where we're getting to a place where we can integrate all of this, we can orchestrate it in a way that makes it possible to get in material, very quickly manipulate it and drive it out. And we can do this in a way where they almost become an autonomous distribution center. So there's very few people that needs to touch this, and especially in a sort of post-COVID world, people will want to know how little does it have to be touched by people before I actually get it on my dinner table. So we're seeing this with these distribution centers. So the big companies in the US that do e-commerce and traditional logistics are working on this. We're also seeing the emergence of factories that can do overnight manufacturing. You can send off a CAD model of what you would like to get manufactured. It will get manufactured. It will be put on a DHL, UPS flight, and it will be in your mailbox tomorrow. So this agility opens up for things that we've never imagined before in terms of doing one-off manufacturing and turn it around very quickly. Of course, we're also getting to a place where we're starting to see even the last mile delivery will be done by drones. So we will see, we have the big companies that are thinking about how can we do this. I live in San Diego. In San Diego, we even have in the city of Chula Vista, where if you call 911, the first thing that will happen is that a drone will take off and fly to the location of the phone call and make a situation assessment. And based on this, it will determine how many ambulances, how many fire trucks, how many police cruisers. So it opens up for a much higher level of agility of coordinating these things in a way that we've never imagined before, which is really opening up new, interesting opportunities. For me as a scientist, it also opens up, what do I do when it's windy, when it's at night, when it's this. So there's a lot of interesting science challenges that are still left to be done here. Of course, when we talk about robotics, there's also a lot of interest in how does this impact the future of healthcare? Where will this go as we see this aging population? So I talked about this earlier. of where we are in terms of delivering these products in a reasonable way to people. And I mentioned before the age pyramid, we will see this grow. So 8 hours per day in aging, and we live longer. So for that reason, we need to figure out how can we help people in their daily lives. Some of the obvious thing is to do surgical robotics, where you can go in and get sort of minimal invasive surgery. It's been a huge success on this. We're also seeing we can use this for knee and hip surgery, where we can go in and do much higher precision than we've seen before. But of course, right now with COVID, we are also seeing a tremendous amount of interest in how can I use robots, for instance, for doing disinfection. So we can drive around robots in the environment, get very good coverage. So here are two examples of two different robots, UVD robots, which is a Danish robot. It will drive around in the environment with the blue things you see on top is UVC illumination. And if you guarantee that you can do sort of 10 microwatts of coverage per square centimeter, then you can say that you basically killed all the germs in that particular area. So we're seeing these being deployed in hospital rooms, in waiting rooms, slowly we're seeing them also getting deployed in hotels, on cruise, on boat cruises. And so there's a number of places where this is getting deployed right now. Heathrow has just deployed them, so that you can basically guarantee that you're not only getting cleaning, but you're getting a level of disinfection that we've never seen before. This is getting enabled by having mapping algorithms that will allow us to explore the entire environment and do this. The one you see on the right is a similar product. It both has UV, but it also has a vaporizer. So you're basically using a vaporizer for some of the cleaning, and then you're using the UV light to guarantee that you killed the germs. So we're seeing this as an opportunity of going after entirely new markets that 5 years ago you said, yeah, that's probably not a good idea. Today, in a COVID transformed world, this is becoming a very big opportunity. At the same time, we're of course seeing these robots being deployed in the homes of tomorrow, where we're slowly getting to a place where people don't live as long in their homes. They will typically stay 5 to 10 years in their home, then they move to their next home. And that has changed the dynamics of how we do this. So we have to think about how do we get robots that can not only be deployed in one home, but that can be deployed in a very large number of different configurations and in different over this. So we very much want to think about how can we integrate it into an intelligent environment and do this in such a way that we can get the right kind of combination. So the question I often get is, so where's Rosie? From the Jetsons family, how can we get a robot like this that can drive around in our homes, give all sorts of services, and enable us to take away a number of the chores that we don't want to do? Still a little bit out. We've seen a number of products getting launched in the environment. So we've seen lots of companion robots that come out, and people would like to do this. Almost all of these have failed because they don't have a high enough robustness. So it's not enough to have a 99% robustness. We need a significantly higher. And to do this, we've not been able to deliver most of these at a cost that people are willing to pay. So most of the products you see here is this, but it's also here very important to go out and see what is it that people want help with. So the robot that you see down here in the lower right-hand corner is a robot that was developed by one of my former colleagues from Georgia Tech, Charlie Kemp. So he went out and wanted to provide a robot that can help people with daily activities. And we sort of imagined, it would be nice if it could bring you a cup of water or, your medication and all of this. So we went out and asked a very large population of elderly people, said, what would you like to have help with? The number one, sort of by a significant margin, thing that people would like to have help with is find my remote control and bring it to me. So this was, and number two was find my glasses and bring my glasses to me. And then significant below this, you got water and then medication. So people wanted to have a robot like what you see here, sort of as a graphical illustration, that can go out and do this. This is being developed right now and at a cost factor where you can actually give it to regular people for something where you don't have to be rich, you don't have to be, it can actually, it's very accessible. So this is coming on the market relatively soon as something that can help you with very simple delivery tasks in your home. We're also seeing this is an example of a company, Seismic, in Silicon Valley, where you're basically taking on the equivalent of a high-end Nike suit. So the Nike suit, and it has built-in muscle fibers, it's weaved into your suit, and then you can activate these. So the thing that you sort of see around here, around his waist, are basically actuators. So if you have a weak back, it will basically enable you to give you sort of back support as you get in and out of a chair, if you're trying to do heavy lifts, if you're trying to do this, and likewise, can it basically empower you? This was developed initially through a DARPA program as an exoskeleton, and where the idea was, could I make a Navy SEAL have a performance that is 10 times higher than what they have today in terms of mobility? And then out of this came one that was sort of a phase where you strap it on, and the other one was this: can I get a Nike suit? It will measure EMG, so measure your muscle activity, and it will use that muscle activity to reinforce it so that you can do this. So we're getting to a point where these products become very interesting, and you can go out and do this. One of the limitations we have here is that battery is still a huge limitation for us in terms of delivering this with a long enough use time so that you could go on a hike in the mountains or something like that. But for home activities, getting up of chair, in and out of chairs, things like that, this is opening up entirely new opportunities that we have not seen before. I was actually on the team that developed the first autonomous vacuum cleaner for the Roomba. This is the Trilobite. This was developed by Lux in Sweden. And the task was, how can we go out and develop a unit like this that can go around, clean in the home for an acceptable price? Today, more than 20 million vacuum cleaners have been sold. One of the big challenges we've seen, and one of our big challenges, is to convince people how should we actually use these robots in a reasonable way. So we actually did a user study where we went out and we asked 100 people, how would you want the robot to drive around? And what you see here on the next is, one of them was it would go around the edge of the room, and then it would move at random, like we did sort of saw also on the first Roombas. And we had another one that was much more energy efficient, much more navigational efficient, where it went out and did sort of a very structured pattern. The best would probably have been to do the equivalent of a Zamboni pattern or something like that. But it did sort of a very structured traversal of this. And all the people, all of them, came back and said, we want the one that has randomized motion. And we were like, why? And said, oh, it's really cool to sit at home and trying to guess where's it going to go next. Get a life. But that was what people wanted. 3 months later, they all came back and said, can I have the other one? So understanding how we do this, it becomes incredibly important for us as we build this robotics technology to understand the human factors and leverage this in such a way that we build the right technology. So one of the things we do to be able to build these is that we map out the environment, which is called simultaneous localization and mapping. How do we map out an entire environment? So basically, the underlying technology is that you have a set of cameras, like you see here, different cameras. I integrate them into a way of doing sort of estimation of what does your environment look like. So in a little bit more formal fashion, we're basically optimizing. We're trying to estimate as the robot moves around, how far did it move, what is its orientation, and we can come up with sort of a mathematical framework for doing this very efficiently and do this even for very large environments. And that now allows me to go in, as you see here in the middle, detect all of the things that's in something like a living room, detect all of the objects. So here will come out and say there's a dining room table in the middle, there's 3 objects on top. So if I was asking my robot to clean the coffee table, it would actually know where the coffee table is, and it would be able to build these. So this is technology that is now very mature. It will run on your standard cell phone, and we can build these models, and that has enabled us to go to places where we've never really gone before. And as part of this, we're also looking at how can we leverage context? How can we leverage this? So it's not like any home is built at random. So if you go in and look at a house like this, we would like to be able to build a model and saying, where's the bedroom, where's the bathroom, where's the living room, what is sort of this layout? That would be incredibly valuable. To do that, what do you do as a researcher? Well, the good news is you go down to your local bookstore, when we had bookstores, or you order from one of the e-commerce sites, get these sort of diagrams, and you go to your undergraduate students and you crowdsource a model for how is this all connected. And when you do that, it will come up for a model that will say, typically, hallways are next to the kitchens, living rooms are next to the bedrooms, bedrooms are next to the bathrooms. So there's all of this cultural knowledge that is encoded by architects. If we can take out those models, we can build a model for what does your typical home look like. It will be different in Europe, it will be different in the US, it will be different in Asia, but we can build these models and actually use this to navigate around in the environment. At the same time, we can go and use this number of text databases, knowledge bases that we can use to go into and figure out what are the typical objects that you would find in houses. So if I'm telling my robot, said, could you go and get me a fresh can of Coke? How is it supposed to know that's in the refrigerator in the kitchen? We need to encode that knowledge into our robots. So we went and we did a number of these things and basically scraped the web for what is the knowledge that's out there. Based on this, it turns out that, which is not so surprising, most cooking items are in the kitchen, most electronics is in the living room or in the office, most food is in the kitchen or in the living room, etc. So we can basically build this sort of contextual knowledge that now enables me to build robots that can go out, navigate through the environment, and if it sees cooking things, food things, then it's probably a kitchen. If it sees other objects over here, it can basically make the conclusion that this is the living room. So we can use this knowledge to make the problem much more tractable by simply using cultural knowledge and contextual knowledge to drive these models in ways that we've not seen before. So here's an example where we drive through the environment, and we've sort of trained a network for this. And based on this, it'll sort of estimate. So you can see in the upper left-hand side, it'll say this is a kitchen. It will drive through this. It'll do a dining room. It will automatically recognize where are the different environments, and we can use this to build much better intelligent systems today than we've done before. We even tried this on a movie like Father of the Bride, and there, even though we'd not recorded it, we didn't code it, it actually gives us close to 100% correct results. So we can use these kinds of knowledge to build very interesting models that we've not seen before, and we can use this kind of contextual knowledge. So in some sense, what we're trying to go after here is how can we build systems that can collaborate with people for everyday functions that, or everyday needs that we have. You can do sort of what you've seen here in terms of the Larson commercial, where you can sort of say, I could go around and annotate everything, which is not very realistic. So the question is, how do I build this sort of fluency between these? And that's where we can not only think about robots, we have to also think about the design of these systems and think about how do we do this in such a way that it works. So, and as we think about design, it becomes very important to think about what is the theme of the environment. Is this a Scandinavian home, or is this a factory? Is it an assembly line? We need to think about the interconnectivity of all the activities. It's not enough to cook food. I also have to think about how do I actually consume the food? How do I clean the table afterwards? And then the dynamics of the social actors. Are there cats? Are there dogs? Are there people? Are there children? And how do I combine all of this? So to give you a very small example of how all of these factors sort of needs to be considered for us to be able to build these systems and study them, then here's an example. It's sort of 15 years old by now. One of my former colleagues, Christensen, was mobility impaired. So for her, so she had to use crutches to walk through the environment. And that made it very difficult for her to do simple things like go to the kitchen and get coffee, because she was using crutches to walk. So where am I going to put my coffee? So we built a robot for her to drive through the environment, go to the kitchen, back for coffee. So basically drive into the kitchen, find her and said, could you give me a cup of coffee for Kirsten? And people were kind enough to put a cup of coffee and put it on there. And in the beginning, people were very scared of the robot. They were, oh, it's driving around in the hallway. It doesn't feel really comfortable. What do we do? Well, we came up with a design solution. So we put this little guy that you see here on top of it. So I'll show it on the next. So we put this sort of aluminum character. It has 4 degrees of freedom. Can do this, can do this, and has 2 arms that can basically put up. And now people were very comfortable with this robot because there was a driver. And it was like, but hello, you know, this is I can tell you the IQ of the driver is 0. But people really liked it because there was a driver. It was clear somebody was in charge of driving this robot through the environment. And because of this, they felt much more comfortable. And this was all levels from, you know, the facilities people all the way up to the professors were very different. And we even tried to move it to sort of other environments. And the conclusions was clear. Once you have this on top, it makes a huge difference for building this. So that's why it's very important for us to sort of figure out how do we do this in such a way that we can build interesting systems for this. So that was sort of an eye-opener for us. Design is such a fundamental part of making sure that you get the acceptance that you're looking for these systems. The other thing that we're looking at is that context is incredibly important. So here, when we talk about natural language, first of all, our language is very ambiguous in many cases, and then if you don't understand the context, so when Lisa talks about pi here, she's of course talking about 3.14159, and so if you understand, she's talking about math. Pi is sort of obvious. Homer, who's maybe not a math nerd, instead is thinking about food, and understanding that the context here plays an incredibly important role for us, because we want to be able to communicate with our robots. We want to be able to talk to them. And especially in a COVID transformed world, we probably don't want to touch our robot. We would much rather use gestures and speech as a way of interacting with these systems in such a way that we can interact with them. And that's where context becomes so crucial for us to be able to do this in a nice way. We're also seeing the use of biometrics, going in and using this so that we can understand what's going on. And here we made tremendous progress. So I would like to be able to build, as an example, an educational robot where I can understand the affective state of humans. And we're getting to a point where we can actually do this today. So when I'm teaching, I would like to be in this quadrant where people are excited and happy. And I don't want to be in this quadrant where people are sad and depressed. So how can I read facial expressions? If I could, like your former speaker, read off the EEG, I would be able to use this to tell what is the affective state of the humans. We can get a pretty good estimate today using camera technology. And now I would like to gamify the way I interact with people so that if they're down here, I want to do some activities that they're very interested in, so I can drive them up into the excited, happy place where people are much more receptive as an audience. So we're getting to a point where we can use facial technology to go in, read their eyes, read their facial expression, read the smile, and use this to drive technology forward, which opens up for having ways where I can read this over time. In the beginning, I might have to give you a lot of instructions to understand how to use a robot, but reading your affective state, I can adopt it over time so that I have exactly the right level of interaction with you to be able to do this. And here again, we can include not only facial expressions, but also intonations of speech that allows us to do really cool things. The last thing I want to talk about is sort of also how do we get into this in terms of doing next generation transportation. Transportation is such an important role. We talked about that 82% of people live in urban environments in the US. The average American spends an hour and 10 minutes commuting to and from work. Pre-COVID, it'll be interesting to see what it's going to be in post-COVID. But it's very important for us to think about how do we build these transportation systems for the future. Of course, building sort of automated vehicles is not a new dream. This is the front page of Scientific American, 1918. People will say, soon we'll have autonomous driving cars. There will be a special lane for autonomous driving cars in the middle of the road. That will sort of be this. So, of course, we're pursuing, how can we build this? Even if I had to sit sort of in traffic for a long time, what if I didn't have to drive the car? So 1898, we had horses, and then 15, 20 years later, we had sort of the first cars, and that was sort of considered a major revolution. It was enabling us to do much better transportation than we've ever done before. So the question is, how are we doing 100 years later? Well, here's transportation statistics for London. 1916, the average speed of transportation was 17 miles per hour. 100 years later, it's 11.8 miles per hour. So because of congestion, it's actually slower to move today than when we had horse carriages. So even if you got the smartest car in the world, it's not clear that you would be able to do this. So even if I gave you what we call a level 5 car, which would be a car with no steering wheel, like Waymo and a number of other companies are trying to do, if you haven't coordinated the entire transportation system, you're still going to sit in traffic and not go anywhere and still move at 11 miles per hour. So it's very important for us to think about this as a system solution. How do we come up with autonomous driving cars that are very different from this? So we need to think about the right way of sort of doing testing of this. So still London, 2015, it's almost as fast of biking as it is to drive around in a car. And it turns out that on the average, public transportation is faster than doing this. This is, again, of course, something that is very contextual. It depends upon where you live and all of this. But nonetheless, overall, we have to think not only about how do I build a smart car, but how do I build a smart system? Because that would also impact, for instance, how we think about sustainability and the environmental impact for these systems. The organization of car manufacturers have built sort of a roadmap where they think car automation is going to go. And basically they're saying right about now, this is sort of what you're seeing right about here, we're getting level 4 autonomous driving. So this is where somewhat, for the majority, the car is responsible for doing the driving, but every now and again, you have to take over. This could be because of traffic work. It could be because of, different challenges. It could be difficult lighting. There's all of these different challenges we still have to address. And they still think that it will be 2030 before we get to a place where you can buy a car and there's no steering wheel inside of it. So we're still some time away because it's incredibly hard to do this. Even though you might say people are not very good drivers. On the average, we drive 100 million miles between a lethal accident. So trying to do that with a car is a little bit of a challenge of doing this. And of course, again, context plays a big role for how you do this. So it's this of how do I build the right user interface? You're supposed to sit there and be able to take over at moment's notice if needed. People are terrible at that. So we need to figure out how can we completely rethink the user interface for this, because this is clearly not the right model for this. At the same time, we're getting to the technology. We have the technology today where we can recognize where are the people on the road, what are the static structures. There's a number of these companies that are using what are called HD maps, which is incredibly detailed maps of the entire environment. I'm personally not a believer in that because I don't think it's scalable to how would I do this for anywhere from Siberia to middle of Nevada to LA and actually build it. So I live on a campus where right now we have 8 different construction projects, which implies that building these maps is very hard because the world literally changes every day. So for that reason, we built a system at UCSD. We built a living laboratory to be able to test transportation technology and deploy it on campus. So there's a lot of the autonomous driving companies that are doing mainly testing on the highway. I don't think we as researchers can compete with the commercial sector for driving on the highway. But once you get off the highway, you get into an urban environment, it's a very different scenario. UCSD is a campus with 70,000 people on campus in a non-COVID period. So 35,000 students and 35,000 faculty and staff. There, the pedestrians will walk at random. So we basically build a system that can drive around, do delivery services on campus, and trying to do long-term testing to make sure that we really understand where are the challenges. How hard is it to make these autonomous 24/7, whether it's rainy or snowy? Don't get that much snow in San Diego, but still trying to figure out how do we do this. So being able to go out, recognize all of the different structures in the environment, drive around. The good news is we now have technology that enables us to very reliably track all the flicker you're seeing here is basically this. We can come up, we can detect where are the traffic lights, we can read what is the color of the traffic light, we can have a driver sneaking by on the inside, say, that's a car, that's a bus. The traffic light, we can detect the pedestrians, and we can even track them and say, are they wearing a backpack? Are they wearing a small bag? All of this we can sort of see. So here you can basically see there's a person, and every now and again it will detect the backpack and the umbrella on these. So we're getting to a point where this confluence of technologies enables us to do things that would be very hard to do before. So we've done a 6 months test of driving around on campus where we detect all of this. We can start to sort of understand the intent of different pedestrians. So we can understand, are they going to stay on the sidewalk? Are they going to cross the road? Are they going to stop? Can we detect the other pedestrian and the other cars so that we can detect the logic of driving in regular traffic? And of course, we need to be able to adopt this over time. Boston driving is different from Washington driving, which is different from LA or San Diego driving. So we need to be able to do this and build very interesting opportunities of doing this. So here's a small video that sort of introduces how we are actually doing this on campus.
Hi, I'm Henrik Christensen. I'm the director of the Contextual Robotics Institute here at UCSD, where we do autonomy, smart robots for all sorts of applications. Right here, you're seeing our automated mail delivery system on campus. So the experiment we're trying to do here is to understand how can we use these vehicles for doing micro, sort of the last mile logistics. And it's interesting to try and test these in a campus environment where we have regular traffic, we have pedestrians, we have scooters. So this opens up a number of new challenges for autonomous vehicles. We bought a vehicle, it's retrofitted so that we can do autonomous driving. It has cameras, it has a LiDAR, and it has various other sensors on there. And we've then programmed it so that it would automatically know where it is. It will detect other things around it, like other vehicles and pedestrians. And then we've sort of developed the logic to enable it to participate in traffic, so it can stay on the road, it will stay behind another vehicle. When we get up to an intersection, it will read what other vehicles are at this intersection, whose turn is it, and then it will use this to drive through this. So it will drive just like a regular driver through traffic, except it's all done by a computer. So the technology we're using this is relatively straightforward. We're using LiDAR, we're doing pattern detection to be able to fit it to cars, to be able to detect, and we're using sort of a combination of neural networks and traditional programming to be able to do the detection of all the things around us. Then we use sort of traditional programming and planning to figure out, given the current situation, how do we determine what should we do next. So we started this about a year ago to build these vehicles, doing the planning. And now over the summer, we've started to do automated mail deliveries. We pick up packages here at the mail center, and then we go right now to Warren and Sixth College and deliver to them. Right now, we are mainly relying on using LiDAR to be able to do this. So one of the things we're doing is that we have 6 cameras on this vehicle, using this to complement the LiDAR, so we become better at detecting cars, become better at detecting pedestrians. We want to be better at determining the intent. Can we predict if somebody on the sidewalk is about to go onto the street surface? Right now, we're only doing mail delivery. We want to get to a place where we can do person delivery, so we can actually have this as a mini bus system on the UCSD campus. So for us, it's been important that we're doing this as a joint project between operations and academics. So we're testing this with a mail center to make sure that we are not sort of delivering fake packages or something like that. We actually want to see how can we help do this in a realistic scenario for real world mail delivery. So that's been very important for us, and for that reason we've had a very constructive collaboration with the operations people at UCSD to test real world scenarios.
So as I mentioned, we've been doing this this was a movie that was recorded in January. We've been doing this for 6-7 months, and testing it out to try and understand where are the use cases, but also to try and understand how do we integrate this technology. So I'm not sure if you saw this, but on the back of the vehicle, it said experimental vehicle, expect erratic driving. Because we actually designed a car that follows the traffic law. In California, you have to stop 2 seconds at a stop sign or at a stop line before you continue into traffic. Nobody in California stops 2 seconds at a stop line. So we actually had to work through this where we stop, people will be honking at us, showing us all sorts of bodily gestures. Who's that idiot that drives like that? So it was important, and one of the things we're studying now is how do I communicate with the other drivers and communicate intent? Am I going to go left? Am I going to go right? Am I stopping in time? So that you can do all of this communication, because otherwise we can never integrate these systems into regular traffic. So I wanted to wrap it up here. So for us, sort of driving robotics is very much using sort of real world challenges. So we're seeing this in terms of our manufacturing, whether it's regular manufactured goods, it's food, it's all of these things. It's getting more and more individualized. You know, my long-term vision is that we will have 3D printers in the back of an autonomous driving truck, and you order something from your favorite e-commerce site, and it will get printed in the truck on the way to you, so that and rich people would be able to have their own sort of facility in the basement. But basically, we're completely revolutionizing how we're doing this because we're using robotics, we're using better sensing, new materials, new computing to be able to do this in ways we've never seen before. At the same time, we're enabling people to get better quality of life by being able to stay at home for an extended period of time, enabling them to do regular daily functions like getting out of bed, getting hygiene, preparing a meal, but also giving them the transportation so that they can participate in social activities, which is so important. And then finally, organizing our infrastructure in such a way that we can, first of all, secure our infrastructure, but second of all, use it to go places where we've not gone before. And that's where context plays such an important role, that you cannot only think about the individual component or the individual system, you have to think about the entire ecosystem and how that comes together to be able to do it, whether it's for e-commerce, for manufacturing, for your daily life, or for transportation. So there we're very much leveraging sort of prior knowledge, figuring out how do we integrate this into a system. And we think very much the future of this is the hybrid. How do humans and robots collaborate on doing this? We don't want the robots to do everything. We want them to empower us to do things that we couldn't do otherwise. We want the combination between soft and hard technologies. We want combinations between machine learning and AI. And then for us, a very important part is we have to be able to do long-term evaluation and understand how does this actually work, not over 3 days or something like that, but for months at a time. So we take changing weather conditions, we take all of these different things into account to guarantee that we can build these systems very well. So of course, at the end, I have to acknowledge, first of all of this research is done by my students, my postdocs, and my collaborators. So I can't take credit for most of it. They do all of the hard work. And then, of course, I have to acknowledge my sponsors, both the various government agencies, but also we work very much with a number of companies, because my attitude is that if we don't find a way of translating it into real world impact in terms of products or in terms of things that are getting deployed, then we're leaving money on the table. And I think we have a responsibility to do good research, but we also have a responsibility to make sure that it's being used for the good of society in a broader context. And with that, I will say thank you very much and hand the word back to Larry.
Thank you very much, Henrik. You can stop sharing your screen now. And let's all give a warm round of applause for this talk. I'm sorry you can't hear it, but I know that people are very appreciative. So we have time for some questions and hopefully some answers. As I mentioned before, there are 3 ways you can ask your questions. The preferred way is to use your Zoom hand if you're on the Zoom feed, and to ask the question directly when I call on you. We'll unmute you so you can. If you're on the Zoom feed, you can also submit on the Q&A feature, and then if you're on FaceTime, on YouTube, you can ask a question by chat, and our social media director, Ann McQueen, will kindly forward your question to me. So let me first say hello to some of the far-flung people that are with us tonight. If I don't mention you, please don't be angry with me. I just want to say especially hello to our people who are listening overseas. We have good friend Frank Robert in Australia, and Zbigniew Sagun, I believe it is, in France. Hello, Zbigniew, and Neil in Colombia. So hi to all of you, and hi to all our many family members. Let me start with a question from Newton Campbell, and then we'll go to a question from Phil Rubin. Newton asks, can you share some thoughts about how data governance should work with respect to privacy for service robots, for self-driving cars? What specific problems have you encountered and thought about in your work with regard to this, that is data governance?
Sure. So, no, great question. Thank you. So this is an area where it's very much an active research area that we're working on, because privacy is such an important part of how we do this. And we have to think about, even for service robots, what can we transmit? What can we do? For the most part, what we're trying to do is we're trying to do things that are sensitive at the edge in such a way that we can encode it to a level where whatever I'm communicating off the robot would not have privacy. So we can do this. The same, we're just doing an experiment actually right now where for some of the driving where you see pedestrians and things like that, the good news is we can give them fake faces. It's very easy now to actually substitute the face for somebody else, so you can't tell who that person is. So we're slowly getting to mechanisms where we have realism, but we're not using this, but also where for something like so if you look at your most modern Roomba as an example, it actually has a camera on board. And I don't want a camera in my home that would potentially transmit what's going on in my home at various times of the day. So there it's very important. We need to do the coding in such a way that the privacy sensitive data will never leave the robot. But it's still, I would say it's still an area where we haven't found the final solution. So the good news is we work with people. There's, for instance, at University of Washington, there's a very good group that does work on privacy and ethics, and we work with them to sort of make sure that we actually can address it in a way where hopefully we can address it before we get this. And at the same time, we have to think about different rules for how can we do this. It's partly been driven forward by the GDPR rules in Europe, which are so much more restrictive. And if you not only want to do solutions that are valid in the US, but also in Europe and elsewhere, you need to be able to do this. So we're working on it, but I wouldn't say that we've found the final solution yet. But there are the good news is we found people in the legal community that find this to be an interesting problem, so we can merge together the legal community and the technical community.
We have a question from Phil Rubin, which we'll take live. Hello, Phil.
Hello. Hi. This is Philip Rubin of Yale and formerly the White House. Good to see you again, Henrik. My question is a follow-up to the previous one and related to that. And I know that you've had a long-term interest in the ethics of emerging technologies. And my concern is there's a growing concerns about things like algorithmic bias, dual use, and I'm encouraging you, and I know that you are, to work hard on exploring and the social context and doing whatever you can to allay the growing fears about emerging technology. So it's more of a plea for things that I know that you already care about and you're doing, but it's growing in importance.
No, absolutely. And I think it's very important, but that's also where I think it's very important that we do these long-term evaluations, because there's still a lot of research that's being done on very limited data sets. And it's just not acceptable. We need to guarantee that we think about diversity, we think about algorithmic bias, we think about how can we weed this in such a way that we do this. And it's a huge challenge for all aspects of robotics, whether it's manufacturing, in the home, in transportation. But I think it's mainly, I think the biggest one is going to be for the service robots. Once you get close to people in their home, we need to guarantee that we have as little bias in there. For that reason, we need these very large scale experiments. But it's also true in transportation that we're seeing this. So I agree, and actually in the new roadmap that's just coming out, the 2020 roadmap, we have an entire section devoted to ethics, privacy, and this. But we also have an entire section related to workforce and unemployment, because there is not a week where people are not calling me up and saying, but you're killing all the jobs, and we need to be able to address this and say it's. I was on a National Academy study where we went through this. I think our conclusion is that we don't have the data to support a conclusion one way or another. Is it creating jobs or is it killing jobs? What we're seeing is that there's a strong correlation between job growth and investments in robotics. And that's typically because we see investments in technology at the same time when we have a growing economy. So right now we have an economy that's sort of in decline, and because of this, we're seeing increased unemployment, but we're also seeing an increased or a decreased investment into technology. So I think the ethics, the employment issues, and then how we integrate it the right way with society is incredibly important. It's at least as important as the technology issues, because if we don't solve those, we will not see adoption.
Thank you.
We have another question from afar. It's from Frank Robert in Australia. Hi, Frank.
I had to figure out how to unmute, sorry. Delightful and very informative talk. Thank you very much, Henrik.
Thank you.
As Larry says, I'm calling from Australia, where I'm on the advisory board of the Australian Space Agency. We've just given a couple $1 million to ground control of robotics in space. There is 150 million more coming, and which we're going to have to figure out how to allocate. And I'm fascinated with your talk, and I'm interested in whether you know of anyone who's looked at the variable latency and bandwidth throughput trade-offs of what you put on orbit and what you put on the ground when you're using a hybrid AI system, because it's so expensive to get anything to the moon and beyond, which is what we're trying to do. Thanks.
So Frank, there is work. So the best work I know about is Deutsche Luft- und Raumforschung, so the German aerospace agency in Oberpfaffenhofen outside of Munich. They've done amazing work, but it's mainly, we've had a lot of these where you're trying to do it. The way people are doing this today, and we sort of consider it to be state of the art, is that you have a system on the moon or wherever your vehicle is, and you have a similar system on the ground, and you basically run them as a simulation, and then you sort of exchange data to compensate for it that they might not be entirely synchronized. So a highly model-based approach is sort of what people are doing for doing this, and gotten really nice results. So Darius Buska at TU Munich, who's working with the DLR, and Sami Haddadin, there are absolutely amazing work. But we also have very good work at JPL. But also we're seeing some of that work not only for space, but also for underwater, where the problem is that being able to do this. So I didn't know this until I started working with the offshore industry. So if you go and look at some of the drilling operations that goes on, for instance, in the Mexican Gulf, the way they communicate with the drill head is that they pulse the mud. So literally, you're banging on the mud, and then you're listening for the Morse signals coming up. And they can do this at about 8 hertz, which implies that coordinating the drill head with what's happening upstairs is incredibly hard. So there's a number of these technologies that we're seeing for space that we are initially exploring in offshore, because we actually there have very similar challenges. But I would say DLR in Germany for this sort of dual model-based approach is some of the best work that's out there.
Yeah, DLR is looking to do that on Europa as well, but not to take up any more airtime. Thank you very much.
Hey, thanks, Frank.
Thank
Good to
you.
hear from you. We have a question now in text on the Zoom Q&A from Mike Helton, a member. He asks, somewhat perhaps whimsically, but more seriously as well, do you think it's possible with today's technology to build a robot that can bounce a rubber ball like a 4-year-old little girl?
So Michael, I'll give you 2 answers just to be the typical academic: yes and no. So in the sense that if that's the only thing I have to do, I can do it. But if I have to actually do a number of other things, no, we're not close. And because first of all, we don't have the dexterity, we don't have the training, and we haven't done this. So I'm sure most of you would know this already, but the average human takes 7 years to become a competent grasper. So it takes us 7 years to get to a place where I can sort of pick up this cup I'll pick up and actually do it. So the definition of competent is that you use exactly enough force to carry it and no more, so that you're energy efficient. And for the average person, that will take us about 7 years to learn. So we have a great set of sensors and instrumentation, but before we've actually learned to do this, it sort of comes back to what Frank was talking about. The problem is that the time delay of doing this control, if I have to send the signal to the brain, get it processed and get it back, the ball would be long gone. So learning this is actually very hard to do. We can do this with robots because we don't have, first of all, the time delay that we have in biological systems. But the challenge is we don't have the cognitive capabilities to handle all of the edge cases. So I would say, if you told me build one that can just do the bouncing of the ball, yes, we can do that. Can I build something that's even remotely? No, we can't. And so it's a very nice project that's been running for a number of years in Europe called ICOP, where the idea was, could you build a robot that would actually be as good as a 2-year-old? So they built a number of these robots, and they were using then learning techniques. So it was done in Genoa in Italy, it was done at EPFL in Switzerland, and a number of these where they studied this, and there was a joint effort between neuroscience and robotics. And the conclusion is that we can't even do a 2-year-old.
Let me just kind of maybe add some color to the answer. As you know, Boston Dynamics just put on the market a $75,000 dog like robot,
right,
that can do some pretty amazing things. And that these are balance type things, and they're getting back on your feet, and they're stability things that, while it's not the same precise motor control and motion tracking that you need to be able to do with a ball with a relatively precocious 4-year-old can do, there's certainly rather remarkable abilities for what is a very strong $75,000 robot. And it operates in unmapped territory. They're not feeding
right, but Larry, you should ask Mark Raybird, who is the founder of Boston Dynamics, who's a good friend, and they will sell you Spot, the mini. So he's doing, he's doing this in the silicate. the videos you're seeing on YouTube where they're doing somersaults and they're doing all of this was the one video out of 30 where they were successful. So this is not something where you walk into the lab and they press the button and it will go and do somersaults.
No, I agree. That's the guy. That's the humanoid. But
right,
the dog
right.
is
No,
more.
the spot they can do, and the first advantage is it's four-legged, so you can get sort of a stable pose, so you can actually do this, and you can do running, and so it's a number of these things in terms of kinematics and dynamics that you can do. It's a super impressive robot in terms of the mechanisms, the actuation, the gearboxes, super impressive. It's not, but if you ask that robot to do the 4-year-old ball bobbing, we would not be able to do it.
Put in a plug that this robots can do, it's
pretty impressive stuff.
Coming along, let's put it that way.
Yeah.
Nowhere near
absolutely
wrong, but it is coming along. All right, so we have a question.
Oh, absolutely.
From Carl Merrill. Hi, Carl. Carl, are you unmuted?
He's still muted.
Is that more and more our whole society.
Okay, could you start your question over, because we didn't hear it before.
This is Carl Merrill, and I'm a member of the Philosophical Society. And one of my concerns is our whole society is ever increasing depending on electronics. And this whole world of robots and automation is dependent on electronics. And recently, we've gotten reports that the sun has been in a relatively quiet mode, but it's going to become more active. And so it's just a matter of time before we have a major solar flare. And so the question is, in designing these autonomous systems and the robots, are we thinking at all about how we're going to protect them against an electromagnetic pulse?
So, good question. And Carl, I would sort of give you the academic yes and no answer in the sense that we are seeing some where we're doing protection of the electromagnetics, and we're of course testing this when we're sending robots to the moon and to all sorts of other planets to see what is happening to these. But the other thing that we're seeing is that we're sort of taking a layered approach. So we're also building redundancy into the system. So even if a single component fails, we are thinking about what can I do to do this. So again, that's as the example of the autonomous driving car. I just had one of my PhD students work on robust deployment of autonomous robots, where he deployed it as a home robot in the environment for 6 months to verify how do we do recovery? How do we build enough intelligence in so that when we get even a temporary or permanent deterioration in performance, we're building in strategies. But the thing is, you can't do it just at one level. So we need to think about how do we do protection of the computing platform? How do we do this with the actuation? How do we do this with the coordination strategy? And the good news is we're getting better and better at this. I wouldn't say it's a solved problem, but there is a lot of emphasis today on how do we build these much better fail-safe systems than today. I would still say if we get a major solar flare-up, you're going to get trouble, because you're also going to get 5G and all sorts of other problems that is really going to be challenged. So we need more work on that. And one of my challenges is that in most cases, doing sort of robustification of systems is not considered good academic work. So it's very hard to publish actually in those domains, because people are like, come on, how hard can it be? We did it. So we need more research in this, because it's incredibly important. If we don't deliver 99.59 performance, we're not being good stewards.
We have a question from Frederica Dorima. She wants to know, in what aspects of decision support do you use neural networks versus planning modeling methods? And is that for dynamic conditions where machine learning training is not sufficient?
So So I'm sort of in the camp of what I would call hybrid AI. I don't believe in purely rule-based planning, and I don't believe in purely machine learning. I actually think we can combine them, and by doing this, we can do much better systems. So one of my arguments is that doing pure deep learning is just too hard. It's too hard a problem, and it's too hard to verify today. We don't have the tools yet to do sort of complete verification of those systems. So where we can do sort of the combination of an overall strategy that we can come up with in terms of planning, but then for a lot of the details, we should do machine learning because it's much better. So I believe in having a model-based approach where a lot of the details are filled in by doing machine learning. But a pure machine learning, I think, is too hard. And then the other is that it's too hard for us to provide performance guarantees. And it's more like, when I delivered my first autonomous vacuum cleaner, Electrolux came to me and said, can you guarantee that we're not going to do a customer recall of 1 million robots? And I was like, oh, now I need to go and talk to my formal computing people and guarantee that I can actually do formal verification on this. And that would have been much harder today if I was using a deep learning network. So for that reason, it's the hybrid AI where we use the benefits of deep learning where you're doing sort of the optimization, but where we have a model, we should use the model.
We have 3 questions from our YouTube viewers. Question number 1 is from Neil. He wants to know, have you ever worked on any in-space manufacturing or robotics?
So I have not worked on anything for in-space manufacturing. Some of my colleagues at UCSD has worked on in-space manufacturing because we have a very close collaboration with JPL. But personally, I haven't worked on in-space manufacturing. I think it's an interesting challenge, but also I think it's interesting to think about. So I used to work with Alain Bertos from College de France, who was interested in other things in space, which was I talked about the ball bouncing before, and we have a very strong prior because of gravity. So if I throw a ball to Larry, he can sort of grasp it with, he doesn't have to use very detailed perception because we have such a good model of friction and all of this. So the question is, if I now go into space, can I do the same kind of experiments? Can I throw a ball at an astronaut? So we did some experiments with Alain Bertos for this, and it turns out that the physics is very different, and we are very model based. So just back to sort of the question we had before, planning versus dynamics. When you change your environment, that significantly sort of challenges your environment. But coming back to the question, no, I've never worked on in-space manufacturing.
Do you have any plans?
So I would love to work on, and actually at UCSD, we're trying to start a collaboration with JPL for the mission that was mentioned earlier on by Frank in terms of going to Europa, where one of the ideas is that they want to be able to fly up a robot, land on Europa, melt through sort of several miles of ice, and deploy a submersible. And Scripps Institute of Oceanography is, of course, an expert on underwater vehicles. So more in the space we're doing this. But Mike Tolley and Joe Wang at UCSD has worked on this manufacturing, and they're much smarter than I am. So I'm going to leave it to them to do this.
Okay, another question from the YouTube viewers. Will Angel asks, the cost of sensors and robotics have come down substantially. What are the barriers to continuing these cost decreases as, quote, Moore's law slows down? Maybe
right. So
the last.
I think I get it in terms of so we're seeing, with Moore's law, and we're seeing it with memory. We're seeing it. For robotics, one of our biggest challenges is energy. We're just not getting fast enough, getting good enough batteries that are sort of small enough that we can do this. So energy is not moving as fast as we want. And I think it's not necessarily cost. What instead we're getting an increase in complexity. So the fact that I can now get to an actuator where I can build in, so we think about, I have 300 mechanoreceptors in every one of my fingertips. And I can do this, and I can do this to do very detailed manipulation of objects. You know, I can go in and sort of do things like this and actually do really cool stuff. I want to use the decrease in price to drive up complexity. I want to be able to get mechanoreceptors that allows me to do this manipulation and all of this. And we're getting to a point where it's within my reach. 10 years ago, that was impossible for me to do. So, but now I'm getting to where I can do these flexible materials. I can build in sensors into this. We can do this. We're talking to a company of the same building cars, but where all of your sensors are built into the body of the car. So the chassis has all of the sensors that you need to be able to drive it. So I don't think we will necessarily go for lower price. I think we'll go for better quality.
I think that actually wraps up the Q&A session. So I want to thank you very, very, very much for joining us and for your informative lecture and for answering all the questions. And I also want to thank Erica again for sponsoring the lecture. And I think at this point you're off the hook. So
thank you, Larry. Thank you for the invitation. That was a lot of fun.
We'll have you back in person as soon as things allow.
Please. Thanks.
Bye. All right. So before we go, a few closing items. First of all, PSW depends on its members. If you're not a member, please join. You can apply for membership via the PSW website. Just go to the upper right-hand corner and click on the blue button that says join in white letters. And that will bring up a screen with a link to our membership application form. And you just follow from there. Your membership application will be submitted automatically, and you will hear from us in due course. The only requirement for membership is a genuine interest in science and a willingness to abide by the Society's rules and enjoy and respect its traditions. If you have any questions about membership, please get in touch with Membership Director Lloyd Mitchell and/or Corresponding Secretary Robin Taylor. Their addresses are on the website. PSW is a nonprofit educational organization, tax exempt under Section 501c3 of the Internal Revenue Code, and contributions are tax deductible to the extent permitted by law and the IRS, at least in the United States. This is the last lecture of the spring lecture series, and we'll be taking a respite over the summer. The fall lecture series is taking shape, and as of now, this is the schedule. We have 2 speakers who have agreed to give lectures in the fall, but we have not yet scheduled the dates, and that will be Robert Bertram of USAID, and he'll be speaking about golden rice, and Wyatt Korf of Howard Hughes Medical Institute, Genelia, and he'll be talking about the project team's approach to research that is taken at Genelia. Wyatt is the head of their project teams. On 23 of October, we have Kang Kwen Ni of Harvard and Harvard MIT, and she'll be speaking on visualization of quantum states of molecules. This is a direct visualization, not a simulation. And then on 6 November, Wendy Friedman of the University of Chicago will join us to speak on measuring the Hubble constant and the fate of the universe. So a light topic there. Also, please, we're coming up on our 150th anniversary March 13th, 2021, we will be having an event to celebrate and commemorate. So please mark your calendars and hold that date, March 13th, 2021. Please check regularly the PSW Science website at www.pswscience.org to keep up to date on our lecture series. And with that, let us note that PSW is run entirely by volunteers. There are no paid staff, and without these volunteers, we wouldn't bring you any lectures, and we wouldn't be having in-person meetings when the time comes again that we can have them. So first, let's thank the people who worked on tonight's show. We have James Heelan, who read and composed the minutes, Ann McQueen, who handled the live chat questions, Robin Taylor, who sets up equipment and tests it beforehand, does the practice session with the speaker and me, keeps me in line, and serves as the Zoom and YouTube director throughout the broadcast. So please, let's have a nice round of applause at home for them. Since it is the last lecture of the spring lecture series, I'd also like us all to thank our PSW General Committee members who carry out the duties and administrative tasks of the organization, our Vice President Mark Clampton, our Corresponding Secretary Robin Taylor, our Recording Secretary James Heelan, our Treasurer Brett Magaram, our Member at Large Connor Nixon, our Member at Large Jared McQueen, who is our Web and IT Director, our Member at Large Ann McQueen, who is our Social Media Director, our Membership Director Lloyd Mitchell, our Special Projects Director Camille Lance. Please join me in thanking them all. Finally, let's not forget to thank our volunteers, Savannah Crawford, Dole Block, Laurel Kane, Robert Thompson. Thank you, one and all. This is the last meeting in the spring 2020 program, and we look forward to seeing all of you in the fall. Hopefully, we'll be able to meet by then at some point. And now we will adjourn the meeting, adjourn the 2,423rd meeting of the Society. Meeting is adjourned.